Hello again, and welcome back to my computer vision series. Today we'll talk about DINO, another model in a long list of Detr-like models like Deformable Detr, DN Detr, and this is the first one that actually achieved the status of state-of-the-art and overcame various old-school detectors like regional proposal networks, HTC, DY-HAD, and so on. So this is a really important one, not because of the techniques introduced, but more because it has finally proved that everything done before with the transformer-based object detection models was worth it, and this is indeed a superior approach to object detection. It is quite a complicated model, so it's not easy to explain from scratch. On my channel, I have a lot of videos that cover previous models, and it so happens that DINO actually builds up on top of those concepts. So it will be ideal if you know what these are before starting this video, but you can also try, and I will briefly try to remind everything used in those models. So to understand what's going to happen next, you need to know what are transformers and multi-head attention, and have some familiarity with Detr-like models, starting with Detr itself, the first one introduced by Facebook Research, then Deformable Detr, DAB Detr, and DN Detr, DeNoising Detr. And here is the plan for today. So as promised, I'll start with just the models overview. It's an interesting thing because it basically tells the story of modern object detection. So we'll start with like, why do we need specialized object detectors? Why we can't use something like ResNet or Swin transformer for that. We'll look at old school models like YOLO and regional proposal networks. We'll go through all the Detr models in sequence. So starting with Detr, Deformable Detr, DAB Detr with dynamic AnchorBoxes, and DeNoising Detr. And that builds the foundation of what DINO is about. Then we'll talk about the actual techniques introduced in DINO, and that's contrastive denoising training, mixed query selection, and look for it twice. Then we'll take a brief look at an extra pretraining dataset used in the model called Objects 365, and finally look at the results and what's next. Okay, so let's start with the overview. So first of all, let's say that we have a classical backbone image recognition model like ResNet. So the way it works typically is we have an input image, and then we pass it through a series of convolutions, typically downsampling the image on each step, reducing the resolution, but increasing the number of channels that we use to pass around information. So at the end of the last convolution, we would have a really small resolution image, like 20 by 20, but maybe with something like 2048 numbers in each pixel represented different detected features. Then we pass all of that through some fully connected layer, and the output is just class probabilities for the specific dataset. So in this case, it's ImageNet, and so it predicts one of 1,000 classes, one of them being a bird. Different backbones actually work pretty much the same way. So Swin transformer, for example, takes in the image, divide that into patches, then perform a series of shifted window attention blocks and patch merge operation. And shifted window attention can be seen as just the transformation applied to the image to arrive at a more processed representation. And then patch merge is downsampling. So it reduces the resolution of the image and increases the number of channels passed around in each pixel. At the end, again, we arrive at a downsampled, processed version of the image with a lot of information stored in every pixel. Then we pass it through a fully connected layer and get our class probabilities. But well, we can actually just swap these fully connected layers predicting the actual classes for anything we want. So we can predict how beautiful the image is, or what is the probability to find adult content in there that can be used for moderation, for example. We can predict the actual bounding box coordinates, and that's called object localization, provided that there's just one object in the picture. So you can have 4 outputs of the model for x, y, width, and height, and just predict where the object is on the picture. And that will work as long as we have just one object on the picture. As soon as we have two, however, that becomes more complicated, because now we have the problem. We can say that, okay, we now have two detection heads, one predicting the bounding box for one object, second one for the second one object. But then how do we match them? So how do we say like which bird is actually matched here or is it matched here? So obviously, like when the network is good enough, that might be one thing. When it is just starting and it outputs just random predictions, it's really hard to say where to match that. And then if you always say that, okay, this head predicts the one to the left and this one predicts the one to the right, then what will happen if they're really close together? And so object detection, in my opinion, is basically about solving this problem. So it wouldn't be a problem if there were always just one object. But as we have many objects and potentially none at all, and a variable number of objects on different images, we now have this matching problem where it isn't clear how to judge the output of the network. It's unclear how to propagate the signal for the network to tell different parts of it where to focus, which object to predict, and so on. And so there were some old school methods of dealing with that. So the probably most famous one called region proposal networks. So it's a two-stage network. It also starts with some convolutional layer that downsample the image, arriving at the processed representation. Here it's called feature map. Then one head will generate region proposals for every region in the image, basically. Then we'll just basically take the top proposals by probability and then pass that through the second stage, which judges how good this proposal is and outputs more precise bounding box coordinates. Now, the problem with this one, first of all, is that it's two-stage, so it's not trained end-to-end. You first have to train the proposal part, then the refining part, and you have to do that step by step, sort of switching back and forth to make sure that they both converge to some state. Finally, it's not really good with duplicates, because if you just judge the proposed regions independently, and so if two of them actually refer to the same object, you'd have the duplicate in the output. And the way to deal with that in reality is typically to use the tool called non-maximal suppression, which says that if the network outputs two objects that are really close together and predicted to have the same class, that's probably just a duplicate, and we just remove that. However, it obviously has false positives. So if you're actually dealing with the image of a crowded people where you do have a lot of objects together in a tight space, the network will not be able to properly identify them. YOLO is similar in this respect, so it doesn't have any two stages, so it's end-to-end now. It passes the image through a bunch of convolutions, and then it has a lot of heads, and each head basically outputs prediction for the specified region. And again, you have the same problem that two neighboring regions might predict the same object, so you'd have duplicates in the output, and you have to remove them somehow. For example, using NMS, which has false positives. You will remove different objects packed together in tight space. So a really cool model called Detr was introduced to handle that. So this is the architecture of the model. So let's go over this to make sure that we understand more or less the structure of the model itself. So it also starts with the backbone, ResNet, Swin transformer, whatever, to arrive at this downsampled processed version of the image. Then these pixels in the image are just flattened out, and positional encoding is added to compensate for the loss of 2D information. Then all of that is passed through the transformer encoder that basically just processes that, arrives at the same shape in the output with a more processed version, more refined version of the image. Then that is passed as a side input to the decoder with some object queries passing as a normal input. And in Detr, the object queries were just normally initialized. And then what comes out of that basically corresponds to detected objects. So it might be a bird, it might be a person, or it might be a special class called no object that says that this particular head is not actually detecting anything. And now the main innovation in this model is the bipartite matching loss. So this loss basically tries to find the best match between what the model has predicted and the ground truth. And so it will basically iterate over all possible combinations until it finds the best one with respect to some loss. And what will happen is it pretty much penalizes the model for duplicates. So if the model has predicted 3 birds, only 2 of them will be matched to some real objects. And then the third one will have to be matched to no object. And so the model will suffer loss from predicting the same object twice. In the same way, it will penalize the model for predicting phantom background objects because the loss has to match, for example, a cat that is not on the picture to no object, which again incurs some loss. But it does not penalize for correct prediction in different order. So if the model just decided to predict this bird with this head and this bird with this head, or in reverse, still, if it predicted both birds correctly, then the total loss is small. Next, deformable Detr. So in Detr, we have this transformer encoder and transformer decoder. And the problem with transformers is and self-attention is that the complexity of the calculation scales quadratically with the sequence length. And for images, sequence length itself scales quadratically with the size of the edge of the image. So we have quadruple scaling on the resolution, basically. And if we look at the actual attention that is going on there, in most cases, it sort of makes sense and it actually focuses on objects themselves. So in this case, it more or less looks at the bird, and then most of the pixels in the background are dark, which means that the attention is quite small. So it's basically saying that I want to look at the bird, but even though it focuses attention on the bird, it still diligently computes all these 0 attention weights for the background pixels, and that does that at every layer. So even though the pixels are dark, even though we do not pay attention to that, we still diligently compute the actual weight and get 0 every time. So on the first layer, we compute it for every pixel for our quadruple complexity, get zeros. On the next layer, we repeat the process, and so on and so forth. Deformable attention says that, maybe we don't need to do that. Maybe we can just focus on the actual object, or rather, instead of just trying to focus on everything and explicitly compute attention between every pair of pixels, let the model decide on its own where it wants to focus attention on, and then compute attention for only those pixels. So it's like swapping from always compute everything and then see what happens to first decide what to compute and then actually compute it. And so it saves a lot of computation. And because of that, so basically it's, instead of being quadratic to sequence length, it's now constant. You always have like 4 points, for example, for which you compute attention. By having that, we can now drastically increase the input feature resolution that we pass into the transformer. And in case of deformable Detr and most of the Detr model that came after that, we can actually use multi-scale, because remember, we start with the image with the highest resolution, and then as we move downwards deeper into the model, we arrive at downscaled version, but a more refined version. So it sort of makes sense to pass all intermediate layers into the transformer as well, because earlier layers, they have higher resolution, which is quite important for detecting precise bounding boxes, but they are less refined. So you can pass all of them, or just a selection of few of them, into the transformer and just let the model compute the attention between different layers as it sees fit. Next, DAB Detr, or Detr with dynamic anchor boxes. So again, coming back to our diagram for Detr itself, Detr, in the decoder, we focus on the decoder now, we have some inputs. And in Detr, we just say that, okay, these are object queries, and we just initialize them randomly and train them along with the model. They do not depend on the image itself, they are just static. And And we think that it works, and it worked with positional encoding, for example, when we just initialize that randomly. However, if we look deeper into what is actually happening in the decoder attention, so in decoder, you would have the query input, and then you'd have the encoder output as a side input. And in all the attention calculations, you'd have three tensors, query, key, and value, that are used in this calculation. And so query and key are used for attention weight calculation, and then value is used to arrive at the final output. So queries are only used for attention calculation, only for that. However, if we look at where Detr actually focuses its attention on, it's really weird, especially at the beginning of the training. So it didn't know where to focus attention. And so what we find out, like, where does it focus its attention? We see that in the beginning of the training, it's completely weird. So it's not uniform. It doesn't have a specified center. It's just sort of all over the place. And so it tries to detect some objects, looking at these different non-intersecting zones like that, until it eventually learns where to focus attention. So it's just saying that it takes a lot of time to learn proper attention, and we can actually help the model with that. And so the way Detr helps is that it says that, let's not pass in just random vectors as queries. We know that what eventually comes out of the decoder is going to be used to predict the class of the object and the bounding box. So we can have the same input. So we can have some tensors corresponding to class that we'll need to predict, and then some tensors corresponding to the bounding box coordinates. And since this query does not really depend on the image itself, we can call these anchor boxes. And now the primary novelty in Detr is that we explicitly modulate the attention layer to use these anchor boxes to formulate attention, to focus on an area of specified size and specified coordinate depending on the actual anchor. And that just gives a much better prior on where to focus attention to. So this is a representation of how that actually looks like. So we started with some anchor. We focus attention on area around that anchor, and then we also update it layer by layer. So first of all, because the anchor itself is not dependent on the image, it's highly unlikely that it will actually be a good fit for a specific object. But then on the next layer, we modify it a little bit to match the object better, and now we focus attention exactly where we need. And then on the next layer, it will be even better, and so on. So we'll keep converging on the actual bounding box of the object, and we modulate our attention to focus on exactly the same spot. And finally, DeNoising Detr. So DeNoising Detr now focuses on the final part of the model, the bipartite matching loss. So this is how it looked like in the normal Detr. And the problem with that is that it's actually not stable. So the same output from the same query might get matched to different objects on different epochs. So now you're matched to bird number 1, and you'll actually be penalized if you predict the bird number 2. And then on the next epoch, you match to something else, and you penalize again. So it basically creates confusing feedback for the model in the state where the model just starts. So obviously, when the model is already good, it's not such a problem. But since we start with just randomly initialized weights, the model is going to be bad, and we have this confusing feedback from different epochs that just slows down the training. And so what DeNoising Detr does is it introduces the second auxiliary loss that is only used during training. So in white here, we have the normal Detr decoder. So we have, and it comes from the Detr, so it also has this concept of anchor boxes and class inputs. And this normal decoder input is going to participate in the bipartite matching loss. On top of that, we add some extra queries that we construct using the actual objects, the ground truth objects, by adding some noise to the class and to the bounding box. And then we pass them through the decoder, like if they're just normal queries. But now, when we get the output, we do not pass them through the bipartite matching loss, and instead pass them through DeNoising loss, which is just saying you have this bounding box with some added noise, and now we ask you to remove the noise, and we judge you on how well you did it. And so this is how it will look like. So in the upper part here is the bipartite matching loss, which might be unstable, which might match different heads to different objects of different epochs. And then the denoising part is always constant. So we always match this head to this ground truth object without instability, without any change from epoch to epoch. And that helps stabilize it, helps train quicker. And then during inference, we just throw all of that away. So it only helps during training. And then during inference, the actual model will behave in exactly the same way as the previous one. Okay, so we are finally starting to discuss the actual DINO model. And we start with a technique that also has to do with the denoising training called contrastive denoising. So let's look again at what happens to the objects and matching in DeNoising Detr. So we have our normal model predictions where we don't know ahead of time what we'll see on the image. And the model basically predicts something, and then we decide on how correct that is or not using the bipartite matching loss. And then the denoising, we have several groups where we just know exactly what we'll expect on the image, and then we solve the problem of denoising. So we have a bird that we have to predict, we add some noise to it, we pass that as an input, and we ask the model to remove the noise and restore the original bounding boxes. And if you think about that, we basically are cheating the decoder into thinking that it solves the same problem in both of these cases. And so by doing that, we make sure that training on the second problem, auxiliary problem, actually helps solve the first problem as well. And these problems are actually similar. So in the normal task, you would start with proposed anchor. Here it's in purple, which might match the object, but not completely probably, because anchor does not depend on the actual image. And then you are tasked with taking this anchor and then updating the prediction to actually match the object. And then in the denoising task, you actually do something similar. So you have this noised ground truth box, which again is slightly off compared to the ground truth object. And then your task is to remove the noise and get the proper bounding box. So the tasks solved here for denoising and for normal task are quite similar, and that's how it works. But then that's not all that happens here. So in normal task, sometimes you would have an unlucky anchor, because again, you'd have like 300 of them, and not all of them actually match anything. And so sometimes you'd have unlucky anchor. And what you want for a query that is unlucky in that way is to not try to predict anything, but just to say that there's no object there. And this is not what we do in denoising. So this is basically saying that in denoising training, we have positives, where we have a good anchor, and we ask the model to, where we have a good anchor, and we ask the model to basically treat it as a good anchor and arrive at the ground truth object. But we don't have the second negative example where the anchor is bad, don't even try to predict anything. And so what we do in contrastive denoising loss is, apart from this normal denoising where we have a bird, we add it as an input with some noise, and then we ask the model to remove the noise and arrive at the original bird. We also have this negative part where we, again, just take the bird, and then we just add more noise, even more noise that it's now completely off. It's a bad anchor. And then we ask the model to explicitly connect that to no object, thus teaching the model to basically ignore unlucky anchors. Next, let's discuss the technique called mixed query selection. So before that, when we talked about denoising Detr, DAP Detr, we assumed that the query inputs with the bounding boxes, we call them anchors, are just static. So they don't really depend on the image. They are trainable, so the model during training will actually adapt them to match the average picture better, but the anchors themselves were independent on this precise picture. And there's another technique called query selection, which actually originated in Deformable Detr, when instead of taking the anchor statically, you initialize that using encoder output. So encoder output is a really refined representation of the image. And so it already contains information about what is there on the image. And then you just apply an auxiliary fully connected layer as a head to get some bounding box prediction out of that. And that can actually be a good predictor of the object on its own. But here we are using that as decoder input, which is basically switching from this static anchor initialization where anchors are independent on the image to dynamic initialization where we get the anchors from encoder output, which makes them more adaptive to what's actually happening on the image. So once again, this technique originated in Deformable Detr, but they don't really pay that much attention to it because that was before dynamic anchor boxes, so it was not formulated as anchors, and probably because of that, it didn't really give that much. Now, since anchors are not just query inputs, they also affect the attention mechanism in the decoder. They affect a lot of things. So now this becomes much more important to properly initialize the anchors. And what we mean by mixed query selection is that we now have two inputs to the decoder. The content input is still static, so it's still trainable independently on every specific image. And the anchor inputs are dynamic and actually depend on the encoder output. Now, the final technique introduced in DINO is the look forward twice. So here is the diagram for it. So the diagram on the left is the look forward once, on the right is the look forward twice. So again, we are coming back to concepts introduced in DAB Detr, Detr with dynamic anchor boxes. So we start with some anchors, either statically initialized or dynamic, depending on the actual image. Then we use those anchors as query inputs, which, apart from other things, helps modulate attention within that layer. And then that layer output basically predicts the correction that we need to apply to this anchor to get a more precise bounding box output. And you would think that the normal way of training all of that would be to just apply the same thing for every layer. In our case, there's usually 6 of them. And then just train this whole thing end to end. Now, the literature actually doesn't focus that much attention on it. And everywhere in papers for Deformable Detr, for DAB Detr, for DINO as well, you just see that they quote that such sort of training isn't stable, basically because by propagating the gradient of this complex computation that modulates attention layer by layer by layer, this training becomes unstable. And to deal with that, originally there was a scheme called look forward once, where you get the anchor, you pass that through a layer, you connect the layer predicts the offset, the correction for the bounding box, and then that itself is connected to a loss. So after every layer, we connect the output to the loss, but then the gradient is detached. So you just copy the tensor to the next layer as an input, and then from there, whatever happens only affects that layer. This is like saying that we are, instead of just training whole 6 layers and the anchors connected to them end to end, we are separating the gradient flow on every layer and just train them independently. And I'm assuming, because it's not really stressed out in the paper, I'm assuming that that helped improve the training. And so what they found in DINO is that that might be not the best case, because this calculation that happens when you start with an anchor, then use that as attention modulation mechanism as well as some prior for the bounding box itself, then you get the prediction out, and then on the next layer you correct that, and so on. And so there is a different scheme called look forward twice, where now two following layers actually affect the gradient flow. And this is depicted on the picture to the right, where the anchors, for example, from the first layer is connected to the gradient of first and second layer. And they did extensive ablation study on that, and they indeed show that this look forward twice connection scheme works better. And I'm assuming that they also tried look forward 3 times and just connect all of that, and it didn't work as well. Now, finally, let's take a quick look at a actual training. So normally when we've talked about Detr, Deformable Detr, and so on, all of them, apart from the backbone, which just usually counts as pretrained weights, are trained on the CoCo dataset. And so the final state-of-the-art version of the DINO model was pre-trained on another dataset called Objects 365. So we can compare that to CoCo dataset. CoCo has 330K images, 80 classes, and then Objects 365 has 2 million images and 365 classes. So it's about 15 times bigger. And DINO also uses either ResNet or Swin-L backbone. So Swin-L is like a heavier transformer-based backbone pre-trained on ImageNet 21K dataset. And we can actually look at both of these datasets. So this is for CoCo and then Objects 365. So yeah, here we can see the rough numbers. So CoCo is 300 images. Objects 365 is 2 million images, so roughly 15 times bigger. We can explore both of these. Let's take an example image with a person, for example, or maybe person and plane. Let's take a look at that. And here we are. So the dataset contains quite high resolution images with plenty of objects in the picture. So that is, again, CoCo. And for many pictures, it contains semantic simulation, so the actual information about which pixels belongs where, as well as bounding boxes. And then Objects 365 is pretty much similar, more classes, more images. And again, we see quite high resolution images, several objects per picture, and the actual bounding boxes for them. So for training and object detection, I would say that these datasets are pretty much the same, but just the Object 365 one is much bigger. Okay, and now finally, let's discuss the results. So to sum up what just happened, basically DINO builds up on a series of Detr-like models like Deformable Detr, Detr with dynamic AnchorBoxes, DeNoising Detr, and all the new techniques introduced in DINO are basically small refinement of what already existed in the literature. So in this case, like the actual scientific contribution, one might argue, is not that great, but it's an insanely important model because it was the first one to actually achieve state-of-the-art status, and it was the first one to show that, you know, this elegant technique with transformers and bipartite matching laws for this solving the complicated problem of matching variable number of objects to predictions of the model that does not require non-maximal suppression, that does not require any post-processing and so on, that this elegant technique, which is easier to argue about, easier to train, it's also possible to achieve better quality. And that is what really proved to the world that this approach is the superior. So here is the learning curves for recent Detr-like models. So we can see here, even though the technique differences might not be that great, like adding negatives there and using query selection and not selecting content queries here, but you can see just how much that affects the actual training. So the final quality to which the model converges is much better, like 2% compared to the previous model. The speed at which the model trains is also much better, so we can see just how much quicker it trains. It's really a good improvement to have these techniques, and it really helps with the training. To sum up, it is, at the time of publication, it was the new state-of-the-art on CoCo dataset object detection. It improved the quality, and actually used fraction of parameters and data size, something like 20% of parameters and 10% of pretraining data size used by previous models like HTC++, with better quality. Another interesting thing is that reported results on CoCo dataset did not use any test time augmentations. So in many previous image recognition models, object detection models, it was typical to use so-called test time augmentations. For example, when you have a picture for which you want to obtain a prediction, you modify it in some way to arrive at 5 slightly different images, maybe cropped out a little bit, maybe with colors adjusted. You do the prediction 5 times, and then you average them all out. And that just helped slightly increase the quality of the final prediction. Because, for example, the different duplicates will not appear if you shift colors a little bit, or if you modify and crop out little pieces of the image. However, obviously, that sort of augmentations are slow and they're not elegant in some way. And it's good to see that with DINO, we can actually achieve better results without any of that. Just throw the image into the model, get out the prediction, and do not apply any post-processing, and just take the predictions at their face value. So finally, we see that the model actually predicts what we want it to predict, and we don't have to correct it in any way. It was also, as I pointed out already, a first pure end-to-end Detr model with no manual heuristics like non-maximal suppression, like static anchor boxes that were actually explicitly coded from the outside. So it does use anchor boxes, but they're statically randomly initialized, or they come from the encoder. And finally, the developers of DINO introduced a cute logo and actually did a lot of things to bring the model to the masses. So they explain how to train it, they explain how to fine-tune it. You can find a lot of YouTube videos about how to use the model in your own projects. So they basically helped popularize the model itself and everything that came before that as well. So this is pretty much it regarding the model itself. I wanted to take a minute to just explain what else do I have on my channel and what I plan to do next. So this video was about DINO, and the very next video will be about reading DINO source code. I also have a lot of videos about modern object detection. So I have a detailed video about YOLO, as well as reading YOLO source code. I have videos about all the previous model in the series. So the first one called Detr, and reading the code for that one, Deformable Detr, Detr, DeNoising Detr. I also have videos about the biggest backbones used at the moment, so VIT and Swin, which are, I would say, most popular. The very next video, I will read source code for the DINO model, so what we've explained today. If you still have some questions about how some of this works, it might be just easier to look into the code. So this is what I'll release next week. Then the very next one after that will be about state-of-the-art model that is relevant right now, called CoDetr. So it mostly uses the same concepts as we've just described, but then again introduces new techniques to make object detection even better. And this model is state-of-the-art right now, so it's unbeaten. So we can be sure that at least for now, these old school models still haven't caught up. We're still ahead if we're talking about transformers and end-to-end object detection. In addition, after that, I also want to make a video about an interesting advancement to DINO called grounding DINO, which introduces a lot of interesting concepts. So DINO, as well as everything we've talked about before, solves this so-called closed set object detection problem. That's when we focus on a dataset like CoCo. We have a limited number of classes, like 80, which obviously do not cover everything you might need about the world, like predicting if it's a dog or a puppy, for example. And grounding DINO instead solves open set object prediction problem. And it is basically a model that merges text and image in the same in one go. So you can provide it with what you want to find, and it will find it for you on the image. So it's really important for two reasons. First of all, this merging of text and image, this so-called multimodality, it's really getting popular at the moment with foundational models for image generation or from solving random tasks that require text and image at the same time. All of them require this cross-modality and information merge from text and image. So it will be good to touch that, good to understand how it might actually happen. Second, it's much better to use something like that in your own projects, because before that, if you talk about DINO, for example, if you actually want to distinguish dogs and puppies, for example, the only way you could do that is to collect the data set and then fine-tune the model, which in turn itself requires you to have machine learning knowledge, requires you to do the fine-tuning, carefully look at learning curves and so on to make sure that you do get the best quality. Grounding DINO can do zero-shot object prediction for null categories. So you can just ask it, hey, is it puppy or is it a dog? And it will provide you with an answer. And so this means that you can plug it into your project and just start using it without having to be a machine learning engineer. You just plug it in and it predicts what you want. So there's really a lot of interesting topics to cover. So see you soon.